Welcome to Data Science with EJD. In this video, we still continue with reinforcement learning under machine learning, of course. And I think this is about the fifth video in that series of videos on reinforcement learning. Of course, when we say that for reinforcement learning, we have an agent in an environment currently in a state with certain set of actions that can take it to another state. So those actions will lead to certain rewards, either negative or positive, that will change its state, and that is how the learning is done in that situation. Okay. So in this video, we'll be looking at, of course, we've seen that, as we look at reinforcement learning, we've discovered that, we have policies, the decision you have to take, the action you have to take are guided by certain policies and things like that. So policy is a big deal, in reinforcement learning. So in this video, our focus is on policy gradient methods. So we go straight to ask the question, what are policy gradient methods? And we see that they are methods, they are a class of reinforcement learning algorithms that directly parameterize and optimize the policy. So they parameterize whatever a policy and they optimize it. And that is, they learn a function that maps states, a function maps states to a probability distribution over the actions available. And they adjust the parameters of this function to maximize expected return. Unlike value-based methods, okay, so it means as opposed to policy gradient methods, we have value-based methods like Q-learning or deep Q networks, which we have considered in previous videos. So unlike value-based methods, which learn a value function and derive a policy indirectly, policy gradient methods learn the policy explicitly. So why do we use policy gradients, right? I mean, we can already see the idea from what I just finished saying. So the key motivations for using policy gradients will be due to the fact that they handle stochastic policies, which are crucial for exploration. They can learn continuous action spaces, unlike discrete action Q learning, and they naturally optimize the objective you care about. That is the expected return. You want the expected return to be optimized. So naturally, policy gradient methods do that. So the formal objective, let's define pi sub theta of an action given a state as the policy, that is, probability of taking action A in state S under parameters theta. All right. And then J of theta is equal to the expected value, as tau approaches, as tau is, uh, approaches pi sub theta, the expected value of r of tau, and that is the expected return over trajectories tau. So the goal is to maximize j of tau over all the possible taus, which are the parameters, where r of tau is the total cumulative reward of trajectory tau. So the policy gradient theorem, from that theorem, we see the key result to be grad theta, that's gradient, right? Gradient sub theta of j of theta equals the expected value of that expression you have there. So this uses the likelihood ratio trick, which is the reinforced algorithm. So the reinforced algorithm is the likelihood ratio trick. And the intuition is that it increases the probability of actions that led to higher returns. So we know the whole essence of reinforcement learning is that you have an agent taking certain actions by trial and error, and then any action that brings a positive reward, is reinforced, while any action that brings negative reward is reduced, right? So in that case now the increase so just like in the case of this policy gradient theorem now, we said we are out to increase the probability of actions that led to high returns. So anything that led to high returns, we want to keep doing that. So an example is the reinforced algorithm, which is about the likelihood ratio trick I just talked about. Reinforce is the basic Monte Carlo policy gradient algorithm. So we initialize policy parameters like theta, we get all the thetas in place, and then we do a loop. We generate a trajectory using using pi sub theta, and then we compute return RT for each time step. And then we update. It's more like when I had this playlist on numerical optimization techniques. So you have this typical thing. So you start with something and then you keep updating until you get your optimal solution. So the update is given by this now. So you have theta plus alpha into all of this expression, leading to the new theta, and then you start the process again. So this is unbiased, but it has high variance, right? Then because of that high variance, we need to think about reducing high variance. Since the estimate can have high variance, improvements to take care of that would include baseline subtraction. So we subtract a baseline BS from return. So we have grad sub theta of J of theta equals the expectation of all of that expression. And then you see this RT minus BS, right? So you're subtracting that baseline from the return. Okay, and then you're updating with that. So a common baseline, which is the value function, leading to advantage actor-critic. Advantage actor-critic is H2C family. And the advantage function, we use A of S comma A equals Q of S comma A minus V of S. So the update uses how much better the action was compared to the expected value. So we get that subtraction. Okay. So in 7, we now have the A2C, the actor. Okay, then we generally talk about the actor-critic methods. So we combine policy gradients, actor plus value function learning, which is a critic. Okay. Actor updates policy parameters using gradients, while the critic estimates the value function or advantage to reduce variance. Popular examples are A2C that we just talked about up there. That's advantage actor critic. And there is A3C, which is asynchronous advantage actor critic. Then we have DDPG, which is deep deterministic policy gradient for continuous actions and deterministic version. Then then we have the PPO, which is proximal policy optimization, and TRPO, trust region policy optimization. In the next video, we'll be talking about some of these things a little bit deeper. Now let's talk about deterministic policy gradients. For continuous control, deterministic policy gradient theorem provides, that expression. This leads to DDPG and TD3 algorithms, right? So the key advantage is it naturally handles continuous action spaces, directly optimizes what you care about, which is the expected return, and it works well with neural network parameterization, and it's powerful when combined with variance reduction and trust region methods. So some key challenges of policy gradient methods, of course, like we've seen before, we talked about high variance. So it needs variance reduction. So we need baselines and critiques. Then sample inefficiency, it often requires many episodes. So if you want to write the code, you can already imagine you're going to have episodes and epochs possibly, especially episodes. Then it can get stuck in local optima, especially with bad exploration. So you're not guaranteed to get the best results. All right. So then it's sensitive to hyperparameters like learning rates, entropy, regularization, etc. So summary of notable policy gradients algorithms, right? I guess okay, well, let's just do this. Then we now go to the policy implementation for reinforce itself. So summary of notable policy gradient algorithms. So we have reinforce, right? It is stochastic policy gradient, and the key idea is simple Monte Carlo gradient, and you have the actor critic, that's stochastic PG plus value, and that uses critic for lower variance, and you have A2C/A3C, which is parallel. So the type is parallel actor critic. So the key idea is you have parallel agents for faster learning. TRPO, stochastic policy gradient, trust region to avoid large updates, PPO, stochastic policy gradient, that is clipped surrogate objective for stable training, and DDPG, that's deterministic policy gradient of policy for continuous control. TD3, deterministic PG, that improves DDPG with double Q learning, and you have SAC, that's stochastic PG, maximum entropy objective for exploration. Okay, so the applications of all of these now, policy gradient methods are used in robotics for continuous control, then game AI, which e.g. OpenAI 5, Alpha Star, then they are used in autonomous vehicles. They are used in finance for portfolio optimization. Any domain with continuous or high dimensional actions, we can also use policy gradient methods. So let's look at Python implementation for reinforce. Okay, as we draw this to a close. Okay, because it takes some time, I have actually run it already, so the results are here, but let's look at the code a little bit. So here, of course, we've been using Gym a lot. The latest version of Gym is Gymnasium, but interestingly, you can actually import Gymnasium as Gym still, and then you can import Torch, import neural networks, torch.nn rather as nn, then import torch.optim as optim. From torch distributions, import categorical. Then you create the class. So mostly here we use object-oriented programming where we have classes and things like that. So we have a policy network. We are used to this already. So you initialize and all that. So here you have some kind of subset. You are creating a class inside a class or something. So, and you have all of this going on here, and then you define some other functions and to return this. So you talk about the environment. So you're talking about the cat pool environment, and you have the state dimension, action dimension. Then you talk about the policy optimizer. Then you also define another a function which computes the returns, right? So you have the rewards and the gamma 0.99 and so on and so forth. Of course, don't forget, I think the gamma we've been seeing this gamma all along. It's very close to one, but it hardly gets to one. It's the discount factor. Yes, that's what the gamma is, the discount factor. So you have R is 0, returns this. So you initialize the return like this. So for R in reverse rewards now, so you have R is R plus gamma multiplied by R, then returns insert O and R, 0, comma R, and you keep doing that. Number of episodes, 1000. All right. And then of course, so you also for episode in range, number of episodes now. So you keep doing that until you get to the number of episodes, which is 1000. So you have the states, you have the log problems and all that. Then while not done, then you have the stage tensor and all of these things going on right here. So then if episode this is modulo division, right? So you're going in 50s, right? It's not equal to 50. Then you print the episode. So instead of printing step by step, you're printing every 50 episode. So we don't have to do 0, 1, 2, 3. So you just print after 50. So that's why since we're going to 1000, so you have episode 0, total reward is 16.0, episode 50, 65.0, episode 100, and you keep going until you get to episode 950, where it finally stops, and the total reward you get is 184, like that. So the key points in the code now, you have the policy network. The policy network, this outputs a probability distribution over actions with soft marks. That is what we define here. The first class the class name is the policy network, and we have that. Then sampling actions. So they use touch.distribution.categorical for sampling actions. Policy network. Okay. And then you have the sampling actions. I'm trying to say, okay, you have categorical props here, So trying to see where sampling actions are. Yeah, policy network. Then forward, the environment is defined here. The compute returns. Then you have the episodes. So you have the categorical thing here, and all that. So then you have the log probability storage, which is needed to compute the gradient estimate. Then compute returns, which is discounted sum of rewards, normalized for better training stability. Then you have the loss, which is the negative log likelihood weighted by return. And you have the optimization step, which is standard touch pi backward plus step. So, you have all of that. You see the loss here. You have the returns and so on and so forth, so that we can now say that the key takeaway is something like this, that the policy gradient methods are a powerful general framework for training agents to act optimally by directly adjusting the probability of taking actions, especially valuable for complex continuous action spaces where value-based methods struggle. And by the way, value-based methods are all the queue thing we've been doing, and the deep queue networks, those ones we considered in previous videos. So with this, we come to the end of this video on policy gradient methods in reinforcement learning, right? So let me know how helpful this is for you. If you have subscribed already, thank you so much. If you have not subscribed, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. Don't forget my code sheets and data sets are available. If you check the description box, you find a link to Google Drive where you can download everything. So you should download first and then start and follow step by step so you can learn very fast. So you can also become a member of my channel. Just click on join and you see different levels of membership you can be part of. and that can present you with some special privileges as a member of the channel, right? So be sure to share the video, like and share, so that more people can have access to the great content I have going on here. So like, come your way again, keep doing data right. Bye.